All right, this is going to be the start of lecture number 3 on the heating thermostat application for our heating systems. And in the first 2 lectures, I had talked a little bit about, locations, installation, anticipators, how they affect the differential, and how to make, those kind of the impact of those adjustments. Cycle rates on the lecture 2 talked about the cycle rate adjustments and the cycle rate adjustments and how that is now set up as either by dip switches or by programming or by screw placement, a number of those things. Talked a little bit about cooling anticipators, as well as some of the industry standards for thermostat wiring and installation, such as whether I should staple them or how many minimum conductors should I need, and then what are those typical conductor applications. So as well as kind of a couple of samples of single and dual transformer systems in it as well. So in this particular lecture, we're going to take a look at some of the installation steps, the required installation steps, and what do we need to do on here. So I think once you've kind of covered the basis and all right, this is the thermostat I'm going to use, and I got to look at my application. So one of the areas that I oftentimes would take a look at is for identifying the height. Is if it's a normal residential, and a typical residential application. Oops, let me zoom in a little bit. All right. And actually, I'm going to see if I can. There we go. Typical residential application. Normally, normally a lot of people put that at roughly somewhere between at a 5-foot level. You can simply go at 5 feet as a. Oops. You could put them as at 5 feet. So that's essentially at 60 inches. Now, there again, you have to look at your customer, look at what they're doing on there. I think the big point that I would make on there is, I would say use caution, for anybody in a handicap environment or handicap home. And you have to take that into consideration. So, again, we'll talk a little bit about those things. So, but that's, I would say, is the typical. Now, there are some people will put it at 48 inches. Again, there is no hard rule that says you have to put it at that. Now, in the handicap accessible, now let's talk a little bit about that. So, handicap accessible applications, let's say you're dealing with maybe a nursing home, or maybe you're dealing with a person's primary residence, and they maybe have somebody that's in a wheelchair, or any type of some sort of any type of prohibitive handicap that's preventing them from being able to do that. I think that's an area that you have to really consider and look at it. Normally, some of those are going to be in the 42-inch area, all the way up as much as 45 to 48 inch is the run. So you could say 42 to 48 inches almost. A lot of this is so dependent on the customer and specs on there. Now, again, if there is a 42-inch high type thermostat, a person that's in a wheelchair would likely be able to make that adjustment. And so that's one of those where you would probably do it. And if I were to say, well, is there one number I'd have to throw in there? And I would probably say the 42-inch would be probably the most appropriate of those things. So this the next part I want to address is, I said look at their building plans and specs. So in some of my classes that deal with looking at the buildings and plans, what'll happen is in a lot of these applications, whether it's residential or commercial, an architect or an engineer, he or she may specify the height that the thermostat must be installed in each of those rooms. And usually they'll look at the plans, and unless you see something that's going to prevent you from putting it in that case, you are, let's call it, legally obligated to install it in the place where they are identifying it. So be very, very careful with that to make sure that you're abiding by those rules. So this isn't one of those things where, I think if you ask most customers when they're in the middle of a building project, they've got so many decisions that they have to make. That's probably one of them that, unless they have a strong feeling one way or the other, I would say usually, the heating contractor just kind of takes over and says, all right, I'll put this at, this such and such a height. So, and again, it could be higher, it could be a little bit lower. It depends on the customer. So, but that's the thing I would do. But when you do commercial and you do some of these applications, that you look in the specifications and they will have notes that will identify they want every thermostat to be at a height. And if it's not like, it may have to meet like ADA requirements. And if that's the case, you will be moving it. So if it's not set up correctly, you will indeed be moving it. So it's one of those where you have to look at that. All right, so let's get into the next part. So, the item B talks about, have a secure backing to the drywall or to the box. And the challenge that sometimes we'll have on here, and this is one of those where there's nothing worse than when you are mounting a thermostat and you have to pull it off of the sub base and all the screws and everything pull right out of the wall. And that's kind of not the greatest of the feelings when you're a tech, because now you just got to spend more time trying to figure out how, you might need another anchor or some other backing behind it. So when you're going to install a thermostat in an application, what a lot of guys will try or encourage people to do when it's possible. So let's say if this happens to be, let's say this represents, that wall. And what a lot of, people will do, here's the next stud, we'll say, all right. So what a lot of times what people will do is they'll set that up where so that what they'll do is they'll mount in that space, maybe like a piece of plywood, like some 5/8 plywood that covers the area where the thermostat would need to be installed. Now, the beauty of that then is you can get yourself, you have room for mounting the thermostat, and I would say definitely never ever less than 3.5, 4 inches, because if you've got a 2x4, let's say think about it, if you were mounting it on a 2x4 handy box, how big would that piece of lumber would have to be? And I don't want it to be so deep that it's difficult to change the wire if there's a need to do that. So that little hole, as far as we're drilling that hole, I would say on there, the hole should be no less, I would say, no less than 5/8, of a diameter hole. I would not skimp on that. You want to make sure you can get the wire through there, and if there's any, it's harder to drill those out a little bit later. So again, I would just look at that. But that's one of those things. Sometimes what guys will do is they will take a 2x4 or a 2x2, but I think plywood seems to work really the best. It's kind of light, but yet it provides you solid, strong backing on there. Would work fairly well. So I've even done it where I took a piece of 1x4 pine and put it as the backing, and it works really good. So mounting the sub base. So in some cases, when you are mounting a sub base, and I'm going to put a little note in here on this thing, is one of the things that we oftentimes will do with sub bases is watch as some allow for, I'm going to say, a 2x4 handy box installation. So if that's the case, if they allow a 2x4 handy box, you might be able to have it set up that way. A lot of our residential thermostats that we use now, they are specifically designed to be mounted to those 2x4 boxes now. Commercially, that's been done for years on there. So, but that's kind of one of those. But there's, you always watch a sub base, always look for the sub base on there. Typically, and I'm going to put on there, requires leveling. Now, they don't normally require leveling, and I'm going to put a note. It's not for operation, but for looks is what it is. So it's really more about the cosmetics. So if you have a sub base on there, that's what you're installing. That's what you're getting set up on there, and then the wire comes out in between there. The other thing that you always want to have a big enough hole for is such that you want to make sure that the hole is big enough to be able to push the wire back into that cavity in there as well. A lot of times when guys are roughing a wall in initially, before everything's all finished and everything on there, and before you're even mounting thermostats, sometimes people will tie a knot around the wire, but it always helps to take some pictures or make a note of it, because it's happened multiple times where a technician would stub a wire out of the wall, and the drywaller never sees it. And so sometimes you gotta, sometimes they don't care, and they'll, depending on who you got working on the job site. But you have to be aware of that. That's sometimes it helps to make sure you've got images and pictures and things like that. So the next part on it talks about, stripping the wires only as much as required. Now, to avoid shorting. Now, I really can't underemphasize that, enough, is that there are times where, I'll go and do a thermostat install, or look at how an existing thermostat was installed, and you got a transformer that burned out, or you've got some other issues going on. And the thing that I want to, excuse me, the thing that I want to point out is that you don't want a ton of wire or of extra conductor that's just hanging in the, out in the middle. You don't want to have that. So usually you want to have most of your conductor covered by the screw or in that particular area. And any additional, you're just risking the possibility of either a short, or having something burn up or smoke a transformer, or a transformer, thermostat, you name it. So you want to be careful on that. So usually they will have what they call a strip gauge, and they will identify specifically how much you need. So like on this one, they're saying for a wraparound installation, they wanted 7/16 of an inch, and if it's a straight in, you don't need as much. So if you strip too much off, maybe you trim a little bit of the wire on there. So that's kind of the typical way that you would look at that. A lot of the new ones are actually like a push. It's like a pin, so you'll push a terminal, and you'll poke the wire in that opening on there, as opposed to, it's more of like a pressure connection as opposed to a screw. So just be aware of that. You do not want to have more than what's absolutely needed, just to minimize that issue. So, all right, item E talks about tighten securely. Tighten it securely. So I totally get, how that ends up being on there. So tighten securely. Don't over tighten the conductors. Now you're typically dealing with, I don't want you to not tighten it, but there's a reasonable amount of tightness. What you have to recognize is these tiny little screws that you're dealing with in these applications, they can't handle a ton of pressure. They can't handle a lot of that. So that's something to be aware of. The other thing I also want to point out too is most screws that we use on thermostats, they would tighten in a clockwise manner. So I want to show you this. So if I were tightening it, I'm turning that screw in that manner. That also means that every single wire that you put under those, they need to be hooked in the same manner so that is under the direction of the screw. So that shows me that as this one right there, you need to loop it in that manner. Now, I can't tell you how many times I've gone on jobs and you'll see a technician put it in backwards. And there is zero reason and there's no reason to do that. The idea is that what you want to do is that as you tighten that screw down, it's going to grab that wire and actually tighten the wire and maybe pull it in even. And if you do it the opposite way, what it does is it actually turns it out and pushes the wire away from the screw. So that's kind of the idea that you want to be a little bit careful on. Next one, on the next part that I want to address on here is the stuffing the extra wires back in the cavity wall. I hate this when guys will do this, is that when you've got extra conductors that you're not using and you guys snip them off and they cut them back. I'm talking way back. So those extra conductors that you have now are completely not usable anymore. So it's just something to be aware of that that can be a little bit of an issue on there. So, any extra wires, what I typically do is I usually will snip them where there's no exposed wire, and I'll wrap them around. But I make sure that they're secure on both sides. It's not like they're going to be touching anything in there. But so when we talk about stuffing the extra wires back into that wall cavity, it's pretty evident and clear on there. So, and again, I'll just put a note on here because I think it's valuable that you do that. What I would say is to wrap them around. Wrap those extra conductors around and back on the cable, on your wire conductor, and then stuff them back in. So that's so important. And again, it has to be accessible. You don't have to tape them all up if you don't want to, but that's kind of one of those. Item G, insulation behind the stat. Now, oddly enough, you'd be surprised. There are actually air currents in some walls. And when a technician drills a hole in a stud plate, in a wall plate on the very bottom, and what happens now is when a person does that and they drill, a hole in a wall, a lot of codes require that hole be stuffed, is what they oftentimes will typically do. So what they will do is it needs to be sealed up. Now, there are in certain applications, and I ran into this commercially a lot of times where and as well as, I guess, residential, especially when you're in areas that have much different temperatures, crawl spaces can do this. But what happens is when you start running into problems where a sensor is picking up a little, maybe 1 to 2 degrees difference in the wall cavity because of the air that's moving through that wall. And what happens is it'll tend to migrate through, just due to temperature differences and air density differences, it will start to, if your room is in a slight negative, it'll actually pull the air current into that hole where the thermostat goes into where the wires go into the thermostat. And you got to be really, really careful on that because it really will create a problem for you. And I've had this happen where just due to the air currents, I've had thermostats where they read 2-3 degrees different, and as soon as I pulled them away from the wall and I got rid of that air current, that temperature difference went completely away. So it's important and relevant in there because that can be an issue. So the note that I put on here is, insulate behind that wall, and so if you have to put a little insulation to plug that hole up, that may be valuable in doing that. Now, of course, the point that I want to make on there is in the, air currents in the wall, what every inspector should be typically doing is they would require that those holes be plugged up, and all of this is about if there would ever be a fire between floor levels, what they don't want to have happen is they do not want to have it where one level of a floor or a basement or a crawl space would feed oxygen to a fire in a different level, and that's one of the reasons why they're doing that. So the note that I'll make, I'm just going to make a note on here is for the sake of doing this is, is holes, should be sealed, and it's really more of I would say a temp and fire prevention. We'll just say on there, I guess, to some extent. What you're trying to avoid is don't allow air to be, or I should say air to feed a fire is typically, and that would be air being supplied into that. So again, you have to be careful on some of that. So again, a lot of the a fire inspector, they will require those be sealed up. All right. Next part. Let's talk about item number 6. Now this one is an important one in here when we talk about setting the anticipator. Setting the anticipator. Now the thing that I want to point out on here is when we want to set anticipator. So if you have an application that has this thermostat and that has the adjustable anticipator, what you're going to specifically do with that is first of all, it's got to be set. You want to typically set it for the amperage of the heat circuit is what I want to point out. And that's typically that's normally what we would do with it, unless there's some other need for that. So let's take a look at some of the methods to properly be able to do this. So this is really dependent on the instruments, on the measuring instruments that you have, and how much current that you're going to have on there is one of the things. So that's kind of one thing that I would point out on here. So when we look at different measuring methods, I think one of the ways that you could do it would be to utilize a clamp-on with that maybe has a 10-turn loop. Now, the 10-turn loop is obvious that it creates, it's creating a multiplier loop is what it's doing. So on the next page, I'm showing this little clamp-on ammeter, as you guys all know. So if I would hook up at let's say the typical thermostat subbase, as an example, and I go to between R and W, what I'm trying to look for, if I'm checking on heating in this case, is that if I end up getting a current setting that's on there, obviously I have to recognize that I've got to make that. I've got to make the necessary adjustment for that. So, for example, and I'm gonna go through one quick example. So, if I were to measure, so in this case, and again, so you measured 6.5 amps as an example. So, if I were to measure 6.5 amps, now obviously, if I measure 6.5 amps with the 10-turn loop. Whoops. So I measured that with a 10-turn loop. And I usually like to do this, and I usually like to let the heating system run for, maybe 2-3 minutes to try to get a good reading of what that is. And that's the normal. So obviously my anticipator, I would just say on here, then anticipator is going to be set for 0.65 amps. is how I would do that. Now, there we go, done. Okay, move that up. There we go. And so if I measure 6.5 amps with that 10 turn loop, I'm going to divide that 6.5 amps by the 10 loops, and it gives me 0.65 amps. If I were to, so the 10 turn loop is nothing more than a multiplier is what it is. And again, you just count how many are in there and you'll do that. Now, there's been times where, you know what, I can only get, 6 loops on my loop that I might have, or I might have a wire that I'm using and I'll just make it 6 loops. Whatever the number of turns are, you just divide that into your reading and that's going to give you that. And anytime, that works good, especially when you have meters that don't always measure inline amps, or you have meters that can do that. So that don't measure it. The other way is if you have a digital multimeter, you would get more accuracy by having the ability. In most cases, you would have more accuracy by creating a multiplier loop and measuring that and then dividing that out to make your adjustment. And again, if you are dealing with thermostats that have programmable cycle rates, then this is not something you necessarily need to know. If you're going to go on these service calls where the customer says, hey, I want that thermostat, I don't want to lose my old thermostat, I like this, and you change the furnace, you're going to need to know how to work with those older ones. So with some of those, and again, those mechanical thermostats, just because we don't have the mercury, the mechanical thermostats still have anticipators in many of them, so you have to recognize. So I think in a lot of ways, I would say my favorite one to do as far as this goes is probably the inline ammeter. Now, most of you might, many of you might have let's say an inline voltometer that has the potential for inline amps. And that's kind of one of them that is probably, that would be one that's somewhat unique on that. So it's very, very obvious on there is, you typically don't expect more than about 1 to 1.2 amps as a maximum. So I would just say use the appropriate scale on your meter on there. So normally, like I said, you have to really look closely at it. Some of these inline ammeters that have inline amps, they might be limited to 0.4 amps or 0.5 amps. And so that what that may do is it literally could blow the fuse. It can blow the fuse in your meter. So what I typically do is this. I like to use my inline ammeter a lot of times, and what I oftentimes will do is I just go into my 10 amp scale and on the higher ampacity, and I just run it that way. And if I have any concerns at all, then I can run either a clamp on, or I can do a number of things. But again, I typically like to use, I'll just put a note on there. I prefer to use the 10 amp scale. Now, if for some odd reason you're pulling, and it's simple because I don't have the nuisance, fuse blowing problems. But if I know what I expect, but if it's close to where I would potentially blow the fuse on the smaller scales, that's going to be a little bit of a problem on there. So that's kind of the norm. So let's talk a little bit about, and on this next page here, this one's showing a small little inline ammeter. And of course, you got to put your meter in series with the heating coil is what you have to do. So whether that means you go to R and W, so be it. If that means you go to take the red and the white wire, or the whatever conductors you're having a heating demand, that's what you'll have to do on there. So, all right, let's take a look at the next one. So the next one identifies, where should I take that reading? So I have a few places. So one of them is you could take it at the stat, right at the thermostat. So I guess I should put T-stat in there. So that would be one. Edit, there we go. T-stat is one. So the T-stat is one of them. In some cases, whoops, typo there. Okay, so the T-stat, you could do it at the sub-base. If the thermostat has a sub-base, that's logical to do it there. You could do it at the, what I'm going to call the low voltage terminal board. So you could do the low voltage terminal board. The low voltage terminal board, I would say on the furnace would be appropriate on there. That would be another place to do it. You can take them in wherever you're going to get an accurate reading to get the current of what's going through that circuit is what you want to do. Now, what I'm gonna share with you is on some of the older boilers and some of the older systems, they used to list on the gas valve, they would say set anticipator to this amperage, and it might be 0.2, 0.5, 0.7 amps. But that made sense back in that day because the furnace or those heating circuits were only pulling that much current. That's what they were doing. That's the reason why I say that. So it's one of those where if you run into that and you see that, just check the current draw of the circuit. Now, when you guys, this is something that I will have you guys do in the lab, where I'll have you wire up a circuit and you're going to measure what the current draw is for that heating circuit to set that anticipator correctly. Now, what you'll realize is that in those older systems, there's a good chance that the only thing you're going to get in that circuit is going to be the gas valve. So, but that is not the case on a lot of the newer systems or the induced draft systems. So it really depends on the heating circuit. The way you can definitively say, what should be in that circuit is going to be, it's really just by going and saying, okay, if I have a heating demand, think about where your thermostat is located and where it's installed. If I have a heating demand, what am I going to have to do? So that's kind of the main thing that I want to point out. So I want to go into item B. So that item B, it says, what are the components that are in that circuit? So what I would say on there is, what are the components that are going to consume any amount of power? So here's what I'm going to say. The T-stat itself may be potentially one of the pieces that's in there. But I don't expect the stat to do much. So I would say the gas valve would be another of the loads, which would make sense. It could be, the ignition module. Okay, let's go ahead and edit this. Whoops. There we go. Okay, so let's get into that. The ignition module, it could be a heat relay. That could be another possibility. And so the heating relay is one that could be another issue. So here's the bottom line is that, the T-stat, I don't expect it to pull much current draw. That should be very minimal. The gas valve is probably going to be the biggest load. Ignition module potentially maybe part of that, and maybe even a heating relay possibly. So especially if you have induced draft circuits, the heating relay may be part of that circuit. So those are the normal things. So if that's where, again, the thing that I would always identify is look, you can look at a diagram and to identify what's really in it. You can look at a diagram to figure that out, and that's really probably the best way to do that. So additionally, the other question is, what else should I be looking at? Well, you might want to wait until the fan starts. And I say that simply because there could be a small, that's given you at least, it's put you at least probably a minute into the sequence. Maybe a minute to 2 minutes into it, and that's the only thing I would say. And then wait until the fan starts, I would say, to get the measurement. And that's the way I would say that. Because, you know, it's possible that there could be some other relay or some other circuit that's in there, but we don't want to get more than what we need in this circuit or more than it's appropriate in there. So that's the reason why I say that. So that's kind of all good stuff in there. All right, so there again, you know, the amperage of what's in that circuit, what we expect in the heating circuit may very well be R and W. So that's a little bit on that. All right, so let's get into the next part of this. So what about troubleshooting some of these applications? What about some of that? All right, so how do I address some of these problems or some of these troubleshooting scenarios? So there's a couple of ways that we could maybe look at it and see what would be the problem with some of this. So let's say that the customer is saying, you know, I think there's too much differential. You know, it seems like it's got too much of a swing. That would be what it ends up being. So if that is indeed the case, too much differential, first thing is it's going to have to be either you're going to have to identify what it is specifically. But the one thing that I would say is, you know, maybe increase the cycles per hour would be the one I would say. If it's a programmable feature, great. If it's you know, however that's being done, if it's cycles per hour, please do that. And the other way to do it is to lower the anticipator setting. Now, the anticipator and the cycle rate are almost one in the opposite. They're going in opposite directions. So by you lowering the anticipator, you're actually lowering the differential. So which is the same as, it's really kind of talking a little bit about cycle rate. And again, earlier we talked a little bit about that, but very important to recognize that. And the customer complaint is, you know, is what you're having happen is what too much differential is, you know, swings are too big. You know, the temperature swings are just too large. And that's what you're trying to minimize and avoid. All right, short cycling, furnace short cycling. All right, so I talked earlier about an example that I had, and I had an application where I had a furnace that was probably easily double the size, way too big. And that was not a good, you know, just not a good thing to have happen. So when the furnace is oversized, what happens is you're starting and stopping so many times. The only way to prevent that furnace from just getting wrecked or killed or damaged and controls start to give you failures is you got to somehow be able to get that cycle rate in a more reasonable range. So, for example, furnace short cycling, the first thing I would identify is, you know, that I would say is, you know, somehow you got to figure out a way, how can I decrease the cycles per hour? You got to look at the thermostat, and you know, and if you have no way to adjust it, or you have no ability to tweak it or adjust it, you may be looking at it may be less expensive and less hassle, and maybe more customer satisfaction is, hey, I can put a new thermostat on, I can make these adjustments on there. So you have to kind of weigh that to what's going to do, what the customer is going to desire. You can increase the anticipator setting. Pater setting. So in probably one of my first applications that I had, it was majorly oversized. I had a conventional, regular old anticipator style thermostat, and I was having issues where I was starting to have inducer motor failures on an application. And what happened was, again, this was an application where the furnace was way oversized for the application. The furnace was cycling, you know, way too much. It would turn on, turn off, you know, in very short run times, and it was just killing the motors and the controls. So the remedy for that, to try to at least have some ability to help with this application, is I literally just said, well, I'm going to take that cycle rate and I'm going to decrease that so that it has to run longer. And but in this case, I had an anticipator. So I just took that anticipator that, my heating circuit was pulling about 0.4 to 0.5 amps, and I just cranked it all the way up to 1.2 amps or 1.0 amps. And on this particular thermostat, I think the max was 1.0. But that was the way I could remedy that. And I actually increased the swings, and I was able to make that work. So it actually was a pretty good remedy. So that's kind of one of those. All right, let's go to the next one here. This next one deals with a burned out anticipator, And you got to ask yourself, what in the world is going to do a burned out anticipator? Well, first of all, I'll give you the most typical way that anticipator would get burned out, and this is an easy one. This has happened to almost everybody at some point in their career, is that you disconnect a wire that was maybe you disconnected a wire and all of a sudden you saw a tiny little spark. Maybe the wire came off, it touched the chassis or did something like that. Every single time that anticipator will be smoked and it is going to burn up. Now it's not going to make a bunch of smoke. It's just going to open it up, and you'll never notice it other than the fact that you're not going to get heating demand. So this is kind of one of those things. So how you end up getting a burned out anticipator is you end up with excessive heat circuit amps is the way that happens. That's the only way that's going to burn out. What it's going to lead, like I said, it could be the spark. That would be one. But in every situation, I can tell you that there will be no heat call. Even though you're telling it to call, there is no heat call. You're going to have no 24 volts to low voltage terminal board, to the heating terminal, I should say. I should change that to W. You're not going to get that. So those are all things that are going to happen. I would suggest at that point is use your inline amps to verify circuit amps. To verify what I'll say is circuit amps during the call. Now, a little troubleshooting scenario that I would suggest. Typically, a technician can use, if you've got inline amps or you have a clamp-on ammeter, you can do this. But an inline ammeter, if you use the 10 amp scale on your meter, you are not going to burn your You're not going to burn your meter fuse up. It would have to take. You would burn up a transformer well before you would do that, and of course you would pick that up. So what most guys would do is certainly do not put a new thermostat in place of it without checking that. So what I would intentionally do is I would check it at the sub base or at the thermostat first and make sure the low voltage terminal board first. I would not use my thermostat until I've rechecked those amps, because something had to happen. Something caused the anticipator burn up. And it had to be excessive heating circuit amps. That had to be the thing that you have to do. So you really have to be kind of smart about that. So I say use inline amps to verify amps during the call. And I'm going to put a note on here. Before installing new stat. Whoops. Is the way I would say that. The thing that I'm gonna note on there, typically, max amps are, I would say normally, let's say 1.0 and to as high as maybe 1.2 amps. I have never seen them higher than that. That would be really rare. So again, if I said, what would be the most that I would ever expect to see on a heating circuit, quite honestly, I really don't expect to ever see more than an amp. They might make it, where you can have 1.2 amps, but that's pushing it. That's really, really pushing it. So you want to be very, very careful on that. All right. Next one, item D. So item D talks about, well, the T-stat's not allowing my furnace to get up to set point. So what do? So the first thing that I would say to check is look at the leveling. So leveling, so what is going on with that? So on your leveling, whoops, done. And delete that. That didn't go. So look at your leveling. There we go. Look at your leveling. Try to figure out if was the thermostat, did somebody relocate it? And obviously leveling, I should put a note on there, that's mercury only. If it's a mechanical thermostat and not some mercury thermostat, it's irrelevant. If it's a programmable, it's irrelevant. It's just cosmetics. It's just what you're looking for. Here's the other one that I talked about earlier. Watch for a low anticipator setting. So anticipator setting is what you got to look at. If you have the anticipator set too low, that will do that. It will actually provide too much heat in that anticipator, and it'll shut the furnace off well before you get to set point. And that's the one thing that I have seen on jobs. So low anticipator setting. Now, it's where this happens is pretty obvious. Where things happen like this is usually where you get a non-heating guy that'll go in and put in a thermostat, or a customer buys a thermostat, they put it on the wall, and they have no idea, like where they should set any of that stuff. And that's kind of the norm on there. That's another one. I would say on there the next one would be maybe your too few of your cycles per hour is another one. So, cycle rate may be too low on there. This is the next one that I would say on here. And I'm just gonna note this one on here. Heat source near the stat is the other one. So watch for that copier. Watch for that. Those things that they put near the stat. They got a computer here. There's anything. If you got another heat source, it will think that it's up to set point way before it really is. And then all of a sudden, the customer's complaining that they're cold in there. And that would be another one of those that you'd have to deal with. All right, so let's take a look at the next one here. Fan does not want to start. What in the world would cause this? So probably the number one issue that occurs is there is no RH to RC jumper. And that's probably by far the most common issue. So you'll get it where usually what happens is on a brand new install, they might be putting the furnace in during one time of the year, and where it's not appropriate to do the cooling. And then what they'll do is what they'll end up doing is they'll say, okay, I'm not going to get this finished, or they'll have no RHRC jumper. And what they do is they don't put the jumper in intentionally. And then when the customer wants to run the fan, that jumper never got put in because they did not want the cooling to run. Now, this is true not only on the mechanical thermostats, but it's also true on the programmable thermostats. So there's some of them where if you have to have that jumper in there, that's the reason why they either may have taken it out, or they can't get the fan run. So the fan is typically driven based on the cooling transformer, and that's normally what it ends up being. Certainly, it could be obviously it could be defective switch in the thermostat. That would be another thing I would do. That defective switch, I would say inside stat. And this has happened. This has happened a few times. This is probably actually quite a common problem where the fan doesn't want to run. The cooling's running, but no fan. And it's one of those where they could be a sub base, it could be that. Either way, you're probably going to be changing the stat. You're going to have to switch it out to do that. But again, you want to eliminate all the other issues. Make sure there's no problem with that. This is one of those problems where I had issues on a power stealing thermostat where the fan was running so erratically. There's times where it never ran, and there's times where it did run, and or it was running when it should not have been running, and that was caused by not having the common, and the thermostat kept sending a small signal to the unit to tell the fan to turn on, and it had no business doing that. So these are all things that can happen on there. So I'll put a note on your power stealing thermostat that if you can avoid using a power stealing stat, I would say stay away if you can. So stay away if you can do that. They're challenging to. There's times where I've had they worked fine, and there's more often than not they give me issues with it, and that's one of the other things. So this is especially true of our other ones, and that can create a lot of erratic issues as well. So, and again, here's the one thing that I would say: ensure you use the common if available. That's the one thing I would say. If you have a common, use it, and on the power supply system. So this will that'll be one of those. And there's obviously other things that can be problem. And I'm just giving you some of them related to some really basic typical applications. So certainly, if I don't have a heating call, what's it going to do? And I'd be looking at, all right, is the thermostat programmed correctly? Is it wired correctly? And obviously you eliminate all these issues. So I think the note that I would just put on there is, ensure, I would say wired correctly is certainly one of them in any application. Ensure, you want to make sure that, this is always a big tricky one. Batteries are good in the stat. So if people have battery powered stats, you got to be super careful. That can be an issue. So it says ensure it's wired correctly, batteries are good. All those basic things can be eliminated. And I've seen applications where customers have thermostats that don't allow a programmable stat, where they don't let the system get up to temperature. There's certain model of thermostats that after 10, 12 years, they would start to show those problems where erratic operation of the heating. Those are system things where if they're running it on AC power and it's not battery, if they've changed the batteries and they still have the problem, you don't horse around with it. Just put a new stat on and you're done with it. And those are all the things on there. And there's other things that I guess we could certainly get into, but those are the basic ones on there. So I'm going to conclude this.